We're going to look at what's called a light clock. And a light clock is really just a thought experiment kind of thing where a light beam could be emitted from one side of the light clock. It could go up, strike the mirror on the top part of the light clock, and then bounce back. And when it does that, a certain interval of time can be recorded. All right, that's just the basic premise of the light clock. So we have a mirror here. And the mirror reflects the light beam. So you emit it, emit light here. It goes up. We have a reflection. And then it comes back. It strikes the original spot where it was emitted from. And then, let's say a second or some interval of time can be recorded from that. All right, so now we know from our past experiences in physics that distance and time can be put together in an equation to find speed. And speed was calculated as the distance divided by the time. All right. If we rearrange that equation, we would see that distance is a product of speed times time. All right, so if we want to know the distance traveled by that light beam, we would call it c times t, where c is the speed of light, and t is the time that it takes for the beam to go up, or go up and come back, whatever. But now we also have to combine this idea with Galilean relativity. And Galileo came way before Einstein, but he had ideas of relativity himself. And he said that the way we would document an event with physics depends on your perspective. What we're going to do is we're going to have it move. We're going to have the light clock move on a spaceship away from Earth. Okay, so here's Earth. And we could have a person standing on Earth. And let's say that the light clock that I've drawn here is in the reference frame of the person who's stationary on Earth. And let's assume a stationary Earth, just to simplify the situation. Stationary person on a stationary Earth. All right, this is his reference frame. We can call it frame S. So by reference frame, I mean that these are his coordinates. And they're at rest relative to Earth, and he's at rest relative to Earth. But let's say that there's a spaceship now, and the spaceship is carrying a monkey on it. Okay. On the spaceship is a monkey. And let's say the spaceship is traveling with a significant speed here. We could call it v. And you could give it a number, like let's say it's half of the speed of light, for example. So it's a significant speed. The monkey is going to carry with him his own light clock. And the light clock is going to be moving along with the monkey and the spaceship with the same speed as the spaceship. So now what we want to draw is we want to draw how the person on Earth would view this situation. You see, spaceship is going to go forward according to the person on Earth's reference frame. So that means that his light clock is going to travel with him. As the monkey travels, the light clock's going to move as well. Let's draw several different positions of the clock over time. And let's say the monkey is just riding on top of it or holding it. The monkey's always with it. See? Now, how does the person on Earth perceive this situation? Like, what really happens when it comes to the light beam? So, the light beam, it can't go straight up and hit the mirror because the mirror won't be there anymore at a later time. So what's going to happen instead is the light beam is going to take a diagonal path. Then it will come back to finally strike the original place where it had left. But you have to compare the two situations, because in the picture on the left, the light beam simply goes straight up, hits the mirror, and comes back. But on the diagram on the right, it takes a longer path, and that turns out to be significant. This is the person on Earth's reference frame. This is how the situation evolves according to that person who's back here on the left, just watching it from the side. But how does the monkey see it? Let's do a new drawing. In the monkey's frame, the light beam simply went up, hit the mirror, and went back, and that's all that happened. It didn't take a diagonal path according to the monkey. So, in order to understand why this is significant, we have to know that the speed of light is constant. But it's not just constant relative to, let's say, some arbitrary stationary planet like the Earth. It's not just constant relative to the person on Earth. It's constant to all people in all reference frames. By the time light travels from the emitting part of the light clock to the mirror over here, that's going to take time t for that to happen, so we're going to use the letters c times t to represent the distance that light travels there. Okay, but in the same time that the monkey thinks the light beam struck the mirror, it couldn't have got that far according to the person on Earth's reference frame. Because if you just look at the length of the path, it would only get about 70% of the way toward the mirror in this other reference frame. Okay, so even though it takes time t for the light to strike the mirror in the monkey's frame, it's going to take a time called t prime for it to strike the mirror in the person on Earth's reference frame. But what I want to do now is take it a little bit farther so that we can use some mathematics on this as well, and we can find a mathematical relationship between t prime and t. Alright, so it's important to know that t is called the proper time of an event in relativity. And t prime is called the dilated time. Now, why is it a dilation of time? As you can see, the path is longer according to the person in Earth's reference frame. Now let's draw something new. Do it down here. I'm going to draw a triangle. And what this triangle represents is, on the lower left we have the point in the light clock where the light was emitted. On the top we're going to have the mirror where the light gets reflected. And I said that this distance here would be represented by ct prime. But I hope it's clear from what we've done so far that the right side of that triangle is going to have the distance c times the proper time. Okay? And we can even give an expression for the horizontal, which would be v times t prime. V was the speed of the rocket ship, if you remember, so that's how fast the light clock is moving from one position to the next. Okay, so that is the situation. Now we want to come up with a relationship between t and t prime. Alright, so that's going to require a little bit of geometry and trigonometry. What we can do is we can use Pythagorean theorem. Alright, so we'll say ct prime squared is equal to ct squared plus vt prime squared. What I'm using there, of course, is Pythagorean theorem, where this is the hypotenuse, and this is one of the legs, and this is the other leg. This one's the hypotenuse, A and B. Alright, so now let's see if we can solve here for one of the variables. I'm going to solve for t prime. So we'll have c squared times t prime squared equals c squared t squared plus v squared t prime squared. Alright, I'm going to move the t prime here over to the other side. we would get c squared t prime squared minus v squared t prime squared equals c squared t squared. Factor out the t prime squared, and we would leave behind c squared minus v squared, and we'll get that. Now what we can do is take the square root of both sides, so we'll just get this. Okay, that's going to give us t prime times square root of c squared minus v squared equals c t. Now I'm going to divide to get t prime alone. Alright. Lastly, I'm going to do just a little bit of algebra on this. See if I can simplify it. I'm going to both multiply by c squared and divide by c squared. Alright. I can pull that c squared out and leave behind 1 minus v squared over c squared. As you can see, the c's cancel here, and we get to a simplified result. Now, remember, the right side is proper time. The left side is a dilated time. Now, one of the things Einstein also said is that V is always going to be less than or equal to C. Okay? Which means that V squared over C squared will never be larger than 1. And so what's going to end up happening is that this factor here has a special name and a special symbol. It's called gamma. This is gamma, and it is sometimes called the Lorentz factor. It's always going to be greater than or equal to 1. So never less than 1. But it's an important quantity in relativity. So gamma is 1 over the square root of 1 minus v squared over c squared. And we'll use it here in a problem.